So how can we leverage the closed form solution of the unitary case for handling the most general basis pursuit problem? It turns out that there are several such algorithms, all known by the common name iterative shrinkage. We shall present one of these methods, an algorithm based on the AdMM concept. We start by explaining the core concept of AdMM in general terms, and then we'll bring it to our needs. AdMM is a beautiful trick in optimization theory based on the well-known augmented Lagrange idea. We are given an optimization task of minimizing the sum of f and g with respect to x. Assuming that this task is hard, we seek an alternative that will enable to separate these two functions. First, create a dummy variable v that is forced to be equal to x and plug it into the function g as shown here. The new problem should be minimized with respect to both x and v. Clearly, the new task is entirely equivalent to the original one. The augmented Lagrange method can turn the constraint x equals v into a penalty term. This term has two parts, a linear expression in which u is the Lagrange multiplier vector, and a quadratic term. Given this expression, we reorganize the new penalty into a single quadratic term. Observe that in doing so, we added u transpose u, but this will have no effect on our solution. Now comes the final step in which we solve the obtained problem by optimizing this expression with respect to x and v alternatingly. When we minimize with respect to x, g does not appear in our goal. And when optimizing with respect to v, the function f disappears. We do have to update the Lagrange multiplier vector in each such round, and this update formula is taken from the augmented Lagrangian theory. This way, rather than solving the original problem, we replaced it by an iterative chain of alternative problems. If these alternative optimization tasks are much easier, the resulting algorithm is of interest to us. Theoretically speaking, the resulting algorithm is known to converge to the optimal solution of the original problem if f and g are convex. This is the AdMM strategy, alternating directions, methods of multipliers. And now let's bring it to our need of solving Hue1 Lambda. This expression has two parts. One will serve as f and the other as g. Applying AdMM on this problem, we get a first step in which we minimize with respect to x, a second in which v is updated, and a third step of updating u. Looking closely at the first step, it is a simple quadratic penalty, and thus its minimizer is given as a linear system solution. In fact, notice that the matrix to invert is constant throughout the iterations. Thus, a pre-calculation of its Cholesky factorization would make the computation of xk easy and fast. We could instead apply an iterative solver such as steepest descent and deploy several such iterations for updating xk. So the conclusion is that the first step is clearly manageable. Moving to the second step, it has a very simple form. We seek the shortest vector v in L1 such that it is as close as possible to a given vector, being xk plus uk minus 1. Come to think about it, this is exactly the case for which we developed the closed form expression. The optimal solution is a soft thresholding of the vector xk plus u of k minus 1. Thus, the overall algorithm is very easy, jumping between a linear system of equations and a near-trivial shrinkage. Here is a summary of the algorithm. We initialize with zeros for x, u, and v, and iterate. In each iteration, we solve the linear system, then apply shrinkage on the given vector, and conclude with an update of the Lagrange multiplier vector u. Iterating this process, we are guaranteed to obtain the optimal solution of the basis pursuit problem.